Why did a canal shorter than 1.5 kilometers trigger years of dispute across Europe? Because before the Vistula Spit Canal existed, every vessel entering Elblag from the Baltic had to pass through the Baltiysk Strait, a sea gate controlled by Russia. Shortcut, long dependence. On the map, the project looks modest, a narrow link between the Vistula Lagoon and the Gulf of Gdańsk, cut through the long Baltic sand spit. In practice, it changed the question from navigation convenience to national control. Kaliningrad Oblast is a Russian enclave between Poland and Lithuania, so the route to Elblag faced outside control at the most basic point, entry from the sea. Poland did not build the canal simply to save distance. It built a separate maritime approach for a port that had spent decades behind a controlled passage. The decision was $450 million for a passage through a spit nearly 70 kilometers long. That investment now compresses into a narrow cut near Nowy Swiat in northern Poland. The question shifts from politics to layout. How does one short passage hold the whole operating route? 1.3 kilometers. On a spit nearly 70 kilometers long, that is a small incision with heavy hardware inside. The route begins at open water on Gdańsk Bay, then enters the cut through the Vistula Spit. The channel is more than 120 meters wide and about 5 meters deep, enough for medium-sized vessels to pass directly from the Baltic side into the Vistula Lagoon. Wind moves across both sides of the strip. Water is visible left and right. The Besics and NDI consortium began construction in 2019. The first phase opened in 2022, while related infrastructure works continued afterward. The route is not just a trench, it includes 2 breakwaters, a movable bridge, and a maritime traffic control center. At the core sits the lock, 270 meters long. Heavy gates close the water chamber. Steel moves slowly, with the dull force of equipment built to stop current, wake, and pressure. Control then shifts from geography to operation. Entry, waiting, locking, bridge movement, and release toward the lagoon. This is the real configuration of access under Polish control. Sea, breakwaters, channel, lock, bridge, control room, lagoon. 4 gates, about 160 tons each, still have to be built into the working passage. The route on the drawing is fixed, but the ground beneath it is not fixed at all. The cut runs through a coastal sand spit with weak geology, open to Baltic waves along the edge of the works. Before any gate can move, crews have to make the sand hold its shape. Hundreds of steel piles go down along both sides of the trench, and teams start deep vibro compaction inside the wet sand. The risk is simple. Water moves the site. Excavators take the first bite from the channel line, then keep moving for many months. Dozens of large hydraulic machines cut through sand, mud, and fine sediment, while heavy dump trucks carry the wet load toward nearby coastal zones. The material does not leave the project as waste. Contractors reuse it as foundation fill for artificial islands, and for the breakwaters planned for the next phase. Wet sand sticks to buckets, tracks grind into soft ground, and every pass exposes another layer that can slump if the edge loses support. The channel is short on the map, but this stage stretches across months of loose material, moving water, and bank protection. Stabilization follows the excavation, step by step. Crews drive steel piles into both sides of the route to stiffen the banks and reduce the effect of water flow through the work area. Then, vibro compaction probes sink into water-saturated sand, shake the grains tighter, and make the ground settle before the finished channel carries load. This method is used on saturated sands because vibration lets grains rearrange into a denser mass. The pile hammer lands with low thunder, and the ground tremor runs through wet sand. After excavators remove soil and rock, teams cover the slopes with geotechnical mesh and a layer of saline soil, because the mesh holds the face against sliding and washout. Baltic spray reaches the edge of the site while the strengthened slopes set the line for the next move. Only after excavation and slope protection do the machines shift toward the sea entrance. With the slopes fixed behind them, the machines move into a different problem. The cut channel was only a gap in sand. The Baltic entrance must hold shape under wave pressure. Loose material now meets steel, concrete, and salt water. The core of the breakwaters begins with material already removed from the canal route. Sand and fill are sorted, hauled, and placed at the sea entrance. Thousands of tons keep arriving while the dark water moves beside the works. Nothing here is waste. Every load becomes the first mass of the barrier. Then the line is pinned. Crews drive large numbers of steel piles into coastal sandy ground, defining the alignment and shape of both breakwaters. Each blow sends a dull vibration through wet fill. Those piles give the young structure a temporary frame, while the outside face takes Baltic wave and current loads. Concrete follows the steel. Along the sheet pile line, crews place reinforcement and pour concrete to lock the profile and raise load-bearing capacity. This is the critical contrast. Recycled sand gives volume, but steel and concrete give control. If the line moves, moves, the entrance narrows, scours, and fails before the lock ever matters. Below the surface, dredging continues. The underwater foundation is cleaned, shaped, and stabilized before the breakwater can take full load. That step matters because loose coastal deposits can deform when heavy armor sits above them. Stabilization spreads the load into a base that does not simply sink into soft seabed. On the outer side, cranes lower heavy concrete blocks in salty wind. A dull roar comes from surf against their edges. These blocks have hollow gaps and openings through the middle, and that geometry lets part of the flow pass through instead of striking a flat face. Less direct impact means less peak pressure on the breakwater, so the entrance is not one wall. It is a stack of materials: excavated sand, steel piles, reinforced concrete, stabilized seabed, and hollow outer blocks. The protected mouth remains empty for now. Beyond it, the lock, the bascule bridge, and shore operations are next. After the canal cut and the dams, the surplus sand is not hauled away. Where does it go? Into a new deposit at the canal entrance. First, wet sand forms a round shape in open water, with wind dragging spray across the surface. Then, crews add soil, rock, and fill from the site, layer by layer. In coastal works, dredged material often builds new shorelines and bird habitat. Later, coastal birds nest there, an island about 5 kilometers wide, already a separate mark on the map, not a dump. Beside the 5-kilometer sand island, the project turns inward. The next object is dry space, cut beside water. The problem is costly. Water pressure never leaves the walls. How is a lock chamber built there? First, workers close the future chamber with parallel double walls of steel and concrete, creating a cofferdam-style enclosure that can be drained below the surrounding water level. Metal meets wet concrete, hard edges. Between the two wall layers, crews install heavy diagonal anchor braces, tying one side to the other before the ground can shift. This is not decoration, it is a rigid contour for a pit that must stay dry while Baltic weather, groundwater, and level changes push against it. If that frame moves, the chamber loses accuracy before any vessel enters. Then come the gates. Hundreds of tons. Massive steel leaves close both ends of the lock, and hydraulic cylinders move them with controlled force. Manual drive no longer makes sense at this scale because the gate must seal evenly, repeatably, and under load. Inside the structure, groundwater regulation pipes and automatic valves manage the chamber without violent turbulence, so the water rises or falls while the hull remains controlled. The lock is no longer an excavation. It becomes a sealed water machine with rules, sensors, and consequences. The valves meter flow, the hydraulics close the steel line, and the electronics watch the sequence. Sensors feed the electronic control center, and the lock holds major level differences without losing operating mode. Once the lock can hold its level, the next conflict is motion above it. A ship needs a clear channel, but the road cannot vanish for long. So the Vistula Spit Canal uses 2 swing bridges, each turning 90 degrees around a central pivot. 1 corridor, 2 claims. The sequence begins before the vessel reaches the crossing. The automated control system starts the opening cycle, and the first bridge rotates sideways. Then the second bridge follows, not in a random gesture, but in a timed mechanical order that keeps the passage controlled. Metal decks leave the road line and open a short window for navigation. Delay becomes the enemy. The choice is not decorative engineering. On a narrow spit, there is little room for long approach ramps or a high fixed crossing. Swing bridges solve that space problem by moving horizontally instead of rising over the canal. This is why the design fits the Vistula Spit. Road traffic and maritime traffic share the same thin strip of land, and neither side gets permanent priority. After the vessel clears the opening, the chronology reverses. The bridge spans rotate back toward the road axis, the locks engage, and the crossing returns to ordinary use. The ship moves into the canal, the decks settle into their original position, and vehicles continue across the cut. With the road crossing back in use, the canal's next dispute moves away from steel decks and into the mouth of the Vistula Lagoon. Who controls the route by which vessels leave for the Baltic? Why does an ordinary canal raise security objections? Because this cut changes access, and access changes leverage. On the chart, the new line is simple. A vessel leaves the lagoon, enters the canal, and reaches the Baltic without turning toward the Russian-controlled passage near Baltiysk. 1 corridor, 1 decision. For Poland, that means direct control over entry and exit from the Vistula Lagoon, instead of reliance on waters controlled by another state. Patrol boats and supply craft can move between the lagoon basin and the Baltic Sea without requesting passage through Russian waters. The map looks clean, but the border water around it carries the weight of permits, naval routes, and political suspicion. Moscow objected to the project by pointing to possible military use and security risks in the Baltic Sea. Warsaw answered with a narrower claim. The canal was presented as a civilian route for maritime access and regional development. That contrast drove the dispute. One side saw a new passage that could support patrol and logistics movement. The other described a local waterway tied to ports, cargo, and tourism. The same trench carried two readings: security file, civil project. Then the approvals slowed. European institutions asked for additional reviews on environmental impact and regional security, and the documents began to matter as much as the concrete. Coastal infrastructure checks often examine bird migration routes, protected habitats, and the movement of sediment along the shore, because a new opening can alter water exchange and sand transport. On paper, these are technical questions. In practice, they delay schedules, financing, and port plans. For Elblag in northern Poland, the canal gives a new argument for investment in logistics, tourism, and local infrastructure. Warehouses, quays, road links, and service businesses gain a reason to plan around sea access that no longer depends on the Russian-controlled passage. But the final file remains contested. European checks on ecology and regional security prolonged the approval process while Russia continued to object on security grounds. After the Polish dispute over approvals and security, the comparison moves to a larger reference point, Suez. On the map, the line cuts between the Mediterranean and the Red Sea, giving ships a direct route between Europe and Asia without rounding the Cape of Good Hope. More than 190 kilometers. A narrow water corridor, dense with hulls, runs almost ruler straight through sand. Opened in 1869, the Suez Canal now carries around 12% of global trade, with tens of thousands of vessels each year. That scale explains the analogy, but not the full charge. The critical turn came in 1956, when Egypt nationalized the canal. From that moment, Suez was not only a trade artery, it became a test of who controlled the route. After Suez put control at the center of a route carrying 12% of world trade, Panama adds a different measure: construction cost. Completed in 1914, the canal runs about 82 kilometers between the Atlantic Ocean and the Pacific Ocean. It cuts away the passage around South America's southern tip, shortening sea routes by thousands of kilometers. But the shortcut begins with a lift. A ship enters the lock chamber in wet tropical air, with muddy water against concrete walls. Steel gates move slowly, and the chamber seals before the water level changes. Then the gates shut. Water from Gatun Lake feeds the chamber by gravity, and the hull rises more than 26 meters toward the inland lakes. Three major lock complexes repeat that motion, step by step, turning an ocean route into a controlled climb through Panama. The price sits in the cut slopes. Crews carve through jungle, clay, and fractured rock, especially at the Culebra Cut, where landslides repeatedly filled the trench. French builders had already failed before the American phase finished the route, and disease control against yellow fever and malaria became part of the project. Over more than a decade, workers moved hundreds of millions of cubic meters of earth and rock, while tens of thousands of laborers died. The bill, measured in today's money, exceeds $10 billion, and trade shifted because the hard part had already been paid in rock, money, and lives. After the expansion completed in 2016, the canal could take ships of up to approximately 170,000 deadweight tons. After Suez and Panama, the Polish case uses another measure: control of the route. Not length, not cargo volume. For Poland, the Vistula Spit Canal carries political weight, because vessels can leave the Vistula Lagoon without using the Russian-controlled Baltiysk Strait. That is the contrast. Ships head to sea by Poland's own route. From that independent route, the final point becomes concrete. 1 kilometer of Baltic Canal became a political statement, explaining its weight in Poland's debate. 1 kilometer. On the map, it is a cut across the Vistula Spit, the sandy barrier between the Vistula Lagoon and the Gulf of Gdańsk. In cold Baltic light, the first visible layer is material: hard concrete slopes, steel gates, metallic railings, and a fairway without extra noise. The project is now viewed as one of the Baltic region's most strategically significant infrastructure works of recent years because it changes control over access. Behind concrete and steel sits sovereignty. Before the cut, lagoon access depended on the Baltiysk Strait, controlled by Russia near Kaliningrad. Regional tension gives that geography a sharper edge because a port corridor is also permission, timing, paperwork, and risk. The canal turns those layers into a domestic passage and a sign of self-reliance. Its price is counted by control over Poland's own sea corridor, not by world cargo volume. The last image is bare, an empty fairway 1 kilometer long leading from Poland's coast to the wider world.